Okay, thank you. It's a great pleasure to have this opportunity to give a talk here. Today, I'll talk about reasoning on knowledge graph towards trustworthy and grounded AI. Okay. First, I'll give the introduction about what's the problem about. Then I'll give 3 types of reasoning methods. Then I'll look forward to what's going on in the next. Okay, introduction. Okay, what is knowledge graph? Everyone knows what is graph, right? What's a knowledge graph? Knowledge graph represents a network of real-world entities. The entity can be objects, events, person, or even abstract concepts. Okay, and it illustrates the relationship between them. Okay, this information is usually stored in a graph database and visualized as a graph. That's why we call it a knowledge graph. The components of a knowledge graph is made up of 2 components. One is nodes, the other is the edges, right? The nodes are the real-world entities. Can be material things and abstract concepts. Edges, that means the links between the nodes, right? Very simple. Okay, here is a very simple example. In the middle, it is a nodes. April Einstein is a person, right? It has many relations with other entities. For example, his father, he is the son of Hans Albert Einstein. And also, you can see these are a very small part of the graph. And each relation is usually represented in this way. One entity, the other entity, and the relation between them. Right? For example, this one is represented by this one. Albert Einstein is it is born in Germany, right? Born in Germany. That's the relation. We call it the head entity. This is the tail entity. That's head, tail, and relation in the middle. Right? Okay. Knowledge graphs have many applications, especially in recommender system, question answering, and natural language processing. Typical applications in industry include this. Maybe I only list 1, 2, 3. I only list 4, right? The first one maybe in the retail, recommending products based on individual purchase behavior and the popular purchase trends across the demographic groups. Based on the gathering information, you can recommend products to the local customers, right? And also in other domains, you can find similar applications. Okay, so what's our task? What's our task? Because the knowledge graph is incomplete. You have only partial observations of the whole graph, right? You want to know more from the observations. Usually, you only have maybe less than 10% of the whole knowledge graph. You want to infer the missing facts. Okay, next. Generally, there are 3 types of methods. The first one is on the embedding-based. The second one is the rule-based. The other one is neurosymbolic approach. Here we at least 4 papers. Our papers. The first 2 is the embedding-based methods. The third one is the rule-based methods, and the fourth one is the neurosymbolic approach. Right? What follows, I will talk about these 4 papers. Okay, reasoning on knowledge graph. First one is embedding-based methods. Okay, what is the embedding-based method? Embedding-based method is try to project a knowledge graph into a low-dimensional space and infer new relations based on embedding vectors. Okay, for a fact triple, okay, you see here, head, tail, and relation. Right, based on for a fact triple, it means okay. I already explained this. Right, H has relation R to T. The head and tail entities are projected into a low-dimensional space, RD. And the relation R is usually defined as a score function. It maps the head and tail entity to a score, right? Indicating that the fact HRT is true or not. It can be 1 or 0 or some number between 1 and 0. Right? You can take it as a probability. Take it as a probability. Usually we call it a true score rather than probability. Okay, here is example. In the embedding-based method, there are four types of tasks. Here you have head entity relation. You want to know its tail, right? You have its relation and tail. You want to know its head, and you have H and T. You want to infer the relation between them. And the last one is to say if this triple is true or not. You want to know it, to determine it's true or not. Okay. Here I give another example here. Based on the solid line arrows, you want to infer the dotted arrows. It is true or not? It's true or not? Or what's the relation between them? Okay. It is it's taken from the Yagro 3 and dataset. Okay. Relations have many inherent properties. For example, they have a symmetry or asymmetry property. For example, spouse of if A and B are spouses, A to B, B to A are both true, right? Both true. Friends of also like this way. Maybe it depends on you take B as a friend, B does not take you as friend. It can be both symmetry or asymmetry, right? This type. And the inversion. Parents of with child of. There are some inversion between them, right? Inversion between them. And also there's composition. Relation has a composition, right? For example, father's spouse is mother, right? This is a composition of the relationships. And also, yeah, here, 1 to n and n to 1. Maybe one father has many children, 3 maybe. It is n to 1. Oh, no, 1 to n, right? But and also parents of child, you can take it this way, right? Here I only list 4. This people, when people study such kind of relationship, they get these properties. Also, maybe you can think that we have more patterns, but you have not discovered yet, right? Here I only list 4. And also here I want to give you, this figure is kind of small. Can you read it? Yeah. This Z paradox is a phenomenon we discovered in one of our papers. It says that commonly here E1, E2, E3, E4 are 4 entities. Commonly in current literature, when they infer relations between them, right? For example, you have E1, E2 has R relation, E3, E2 has R relation, E3, E4 also has R relation. In current model, if these 3 lines are true, in their model, they usually infer that this one is true. But in fact, it is not. It can be both true or not true, untrue, right? Here, I give you an example from a database. It tells that sometimes it can be true, sometimes it's not. So when you design the relation scores, you have to take very carefully consideration into it to find out the model has the ability to infer it's true, can make it to be true or not. Both are possible. But before we find out this phenomenon, people in current model, they always, in most of the models, they always infer this one as true. Okay. Here, I only list maybe 11, 12 methods here. If you Google around to find it, there are maybe currently it's more than 30 models. They have a head, tail, and relation. You can give many scores, right? Many scores to see where the fact is true or not. But you want to preserve all these properties, right? All these properties. The last 2 methods are ours. This one, our method. This one is also ours. Okay, we can look at this table. This has many properties, right? Only the last one can model all relation patterns. This one is published in maybe 4 years ago. That's the time we didn't find this column yet. Okay. I'll give you some examples, some numerical examples here. Okay. For M Queen E, according to this 4 years paper, it is in this task. Maybe I need to explain what does this mean. Heat at n, it means that if you have a task, for example, you have a head entity, you have a relation, you want to know the tail, right? Heat n means that you can find maybe heat 1, maybe the first shot. If you are right, you're right. Okay. Heat 3 means that the right one is among the top 3. Heat 10 means the right answer is among the top 10. If you are right, you get one score, right? Here, compared to other methods, M called E is the best. And also in this one, in this task just mentioned in the last one, to determine if a fact is true or not, right? In previous method, the best one is only give you 33 in this data set, and our method gave 84. This is okay. And also in this task, this paper is published last year or this year. I don't remember. It is the best among the embedding-based methods, and also gets the best score. The I'm coding in the 4 years paper maybe also got the second best or third best results. Okay, that's the embedding-based method. It's very simple, right? Okay, the pros and cons. The method is very simple. You propose a score. It preserves patterns, right? Then you can run tests to see what's the result you get. It scales, because for a very, very large database, embedding-based method is very simple and effective. Right? Simple, effective, it scales to a large database. But as you can see for now, it has many patterns of the relations. You can never find all patterns. So what's the solution? Right? You can handcraft the score, preserve this pattern, that pattern one by one. But it's very hard for you to model a relation to find all patterns, preserve all patterns, right? People try to say, oh, a relation is a unknown functions. They try to use a neural nets to model the relation. But if you did it that way, the relation patterns of this cannot guaranteed in theoretically, right? Also, okay, I'll skip the embedding-based method. Let's go to the rule-based method. This method, maybe is Mingming here? No, he'll talk about it later. This method currently seems to get more and more attention here in this area. Okay, in order to introduce this method, I need to give you many backgrounds. First, I need to talk about first-order logic. What is first order logic? First order logic associated a knowledge base. You can take it as maybe a knowledge graph. Okay, it's a expression based on the relation in K. It's usually represented in this way. If you are not familiar with logic, it's very complicated, right? It seems to mean nothing. But this one is equivalent to this one. What does it mean? If some facts holds, you can draw some conclusions. Then it's very simple, right? You can get it. These facts, maybe as assumptions. If all these assumptions holds, you can got some conclusions. This conclusion can be A or B or true, right? A or B or true. In first order logic, these two are equivalent. Okay. In this type of rules include the relation patterns we mentioned above. the symmetry, asymmetry, inversion, composition, all these kinds of rules, relation patterns can be can be represented in this form. From assumption to conclusion. Okay, I'll give you an example. Okay, for example, if x, if x, y are friends, and also y like z, maybe z is a product, right? I can infer maybe x also likes z. Maybe z are sports, right? Y likes playing football. Then also x also likes playing football, right? Now I can explain to you these two are equivalent. It means what? It means x in a word. I will explain you what is a word means. It means in some abstract word, you assign some facts. You have all kinds of facts, right? If you assign some facts to be true or not, you assign all the 1, 0 variables to all possible facts. Then it's called a word. Right? In some kind of word, it means that x likes z, or x, y are not friends, or y did not like z. This one means this implication. Okay. Rules are not necessarily simple as above. In fact, any subgraph repeated appears in a knowledge graph can be a rule. You have knowledge graph, you find some repeat patterns. It can be potential to be a rule. Okay, what is grounding? Here in this rule, x, y are variables. In the real knowledge graph, you have this x, y are entities, real entities. For example, x is Bob, x is Anne, B is Bob, Z is dog. You can also replace that as a cat or something else, right? This is called the grounding. Very simple. But you can think that for a rule, for a very long rule, if the knowledge base is very large, you have many entities and many relations, all kinds of groundings, right? The groundings can be overwhelmingly large, right? Especially for knowledge, especially for huge for large knowledge base. Actually, this is the bottleneck for current solvers. If you want to solve such kind of problems, they have to do the grounding first. For large knowledge base, even grounding them into the memory, into the disk, is impossible. Okay. Okay. Morphologic network. If you want to solve such kind of problem, you have a cost function. You have an optimization target, right? This is the target. It's a joint probability. Okay, I'll read this very similar. A full assignment. Assignment means a grounding to all facts. Is called a possible word. The assignment to the both observed facts, and also the unknown facts determines a possible word. Given m first-order logic rules, you can have many rules, right? The Markov logic network encodes the possible word, the observed facts, and the hidden facts as a random variable, defines distributions as this one. Here, WI is some kind of width. If the rule you are 1% sure this rule is true, it's a hard rule. This width is large. In some rules can be, sometimes it's true, sometimes it's not. Then this width can be small. IOI, what is IOI? IOI means I means the S rule. It means how many times this rule is satisfied. Right? How many times this rule is satisfied? Your summation all of this and take take S is potential. This probability, joint probability, is proportional to this one. You can imagine that it has a very has an integration also in the among the all possible world of this one, and you integrate the whole world, all possible world. You have the numerator below here, right? And also this one ni. Ni means how many times this rule is violated, how many times it is violated, right? This one. In the end, when we do the optimization, we are using this form. You try to say, I want to maximize this joint probability, then I want to minimize this one, or take this potential. Okay. Markov logic network defines a probability distribution over a set of relation data, right? It's relation data with the first order logic rules. MLN assigns higher probability to the words that cite more grounded rules. If this fact is cited many times, it assigns higher probability to it. MLN is elegant in theory and effective in practice, but MLN suffers from an efficiency issue due to the huge number of groundings. Okay. Okay. What's our optimization task? MAP inference. Given the assignment of the observed facts, the maximize probability inference for the unobserved facts to solve this kind of problems. It's a O1 optimization, discrete optimization, right? It is essentially a binary programming problem. And it is well established that the problem 1 is actually a NP-hard problem. Numerically, the work SAT algorithm is usually used to solve such kind of problem approximately. This algorithm is actually very simple. You pick some facts, take it out to see it is 1 or 0. You randomly flip a sign. It is 0, 0, you flip it to 1. If it is 1, you flip it to 0 to see if this value get smaller or larger. If it gets smaller, keep it. If it's not, you keep it. It's very simple algorithm. But in order to perform such kind of problems, okay, it needs to grounding. Problem 1 has H is the unobserved facts, right? This kind of binary variables. It can be in the order of this one. E is the number of entities. R is the number of relation, right? Number of relation. Under the open world assumption. Okay, I need to explain what is the open world assumption. Open world assumption means that in the observed world, you also assume sometimes your observation is wrong. So sometimes your observation is wrong. Right? And consequently, even storing such a large number of variables can be prohibitive for large-scale knowledge base. The entities can be billion, for example, Relation can be maybe thousands. You can imagine how large number of variables are there, right? And also this is a variable, right? If you are grounding the rule can be long sometimes. You substitute the relations, the O10 into the rules, the grounding can be even larger, right? The grounding phase is usually both the computational and storage bottleneck for existing ML inference software, and prevents them from scaling up to large-scale knowledge base. So our solution is to say that we want to still use work SAT algorithm to solve the problem, but we don't want to do the grounding. So we we look at the algorithm and see how to perform the algorithm. Then we find that we only need 3 subroutines to make the method work. We skip the grounding phase. Look down to see we need to only these 3 subroutine. What's the subroutine? The first routine is to say I want to randomly generate a valid clause, or maybe this clause means rule. I want to see which rule is validated. Pick one, maybe pick 2. Take it out. As then I use another subroutine to select the fact in the chosen valid clause. This rule is validated, and I want then I see what facts are involved in the rule, and take it out and flip. Then I flip its sign. Flip its sign, just as work activity algorithm. Then I use another subroutine to efficiently compute, update the cost, update your target function. If we have these 3 subroutines, then the algorithm is able to work. Right? So instead of storing all grounded clauses, or maybe rules, we only maintain the clauses, the rules that are validated in the memory, and keep updating the validated clauses during the random flipping procedure. We only store a small partial of the validated clauses in memory. We don't need to store all of them. Okay. Then why this method works? We make this assumption. Do you remember what's this one? That's the entities involved in the assumptions. That's the entities involved in the conclusions. It's very natural, right? When something happens, you get a conclusion. The conclusion should be a subset of the assumptions. Should not exceed, go out of when the sun is sunshine, you'll see another something very, very unrelated stuff. You don't want to get that, right? You see when the sun is bright, I want to say the temperature is warm, right? I don't want to see what I wear like shoes, maybe something like that. Very unrelated stuff. Maybe this one means this is a very natural assumption. Then we have this theorem. The theorem says that the number of validated clauses is upper bounded by this value. And what is about this value? This value means KROH means is the number of positive facts associated with the relation R. You have many billions of entities. You have a relation R, right? But only a small number of them have the relation R. Not all of them. Not all of them. That's why this one is very sparse. Then that's our conclusion. This one is far less than the E square. So that's why we call it sparse validation, right? Sparse validation. Okay, that's the results. These 3, before our method, these 3 is very popular. They have the dominant software in this area, MLN area. For this, this is a very simple data set, a kinship data set. If you are familiar with the area, it means that you have some people in database. What's the relation between them? Father, son, and wife, something like that. It's very, you can generate this database as large as you want. I just want to use this database to show the performance. Their performance are quite similar, but the running time differs dramatically. When it's only 1,000, Taffy use approximately 1 minute. These 2 fails, but ours only use milliseconds, right? When it comes to 100,000 entities, all 3 methods fails. Our method only use 33 seconds. Okay, and also in this practical database, it's this 3 database. All these 3 methods fails. All these 3 methods, ours only use maybe only in minutes, or last one. Oh, this is the accuracy. This is the accuracy, not the time. Running time is this database is 10 hours. It's a very large database. Even you with our method use 10 hours. With this, the two small ones, it's only 5 minutes or 30 minutes. The accuracy before our method, all this database are not is impossible for MLN-based methods. MLN-based method. For the first time, the pure MLN method can scale to WN18 and Yago 310 in the open world setting without making any approximation tricks. Before our method, people I want to solve this problem. They have to make some assumptions to simplify this problem in order to make their method work. Otherwise, it is impossible. Right? Currently, this method is the fast one. MLN-based method in the literature. This work is published maybe 2 years ago. Okay. Console for MLN. As you can see, this one, x square r, is very memory inefficient, very large, right? Recall our KGE knowledge embedding-based method. Our memory cost is only this one. DE is a dimension for store entity. DR is the dimension for representing relation. It's linear in entity and number of entity and the number of relation. But this one is polynomial. It's quadratic or linear in R. It's very large. So we want to, in our neural-based method, we want to take both memories from both methods to develop a more efficient and more practical methods. Okay, neural symbolic approach. How many times? Okay, diff logic. This method. Okay. Recall knowledge-based, embedding-based methods. You have a score for facts, right? You have score for facts. Then you can use the score to determine how well a fact triple is. Is this fact true or not? Or some kind of, you can give a sign and a true value to see if it's 0.9, it is probably true, right? It's 0.1, it's unlikely true. Something like similar to the probability. Here we use a soft logic to do this. Later I will tell you what is soft logic. And also, once you have this fact, the true score of facts, you can determine if the rule is satisfied or not. You have to give a measure to determine this rule, because the fact is not 1 or 0. It's something between 1 and 0. Then you need to say, when this fact is 1.5, you take all this these facts together. You want to see if this rule is satisfied or not. Then we introduce a function to do the measurement. Once this measurement is given, we can do the joint probability. Okay. What is soft logic? Here I have the truth table for logic operators, right? Conjunction, disjunction, negation, all this kind of truth table. The truth table. If you are familiar with this one, it's simple. But currently, our variables are not 1 or 0. It is between 1 and 0. Right? You have to do the extension from this truth table to soft logic. The most popular one is that the L logic is given by this one. If the PQ are 0 or 1, this extension is coincides with this one, with this table. But if it is between 1 and 0, it also means something. Right? Okay. Truth table, soft logic. Then this is the distance to satisfaction for a rule. This one. If you're familiar with machine learning, this is ReLU, right? ReLU function. It's a ReLU function. This distance is within 1 and 0, and the smaller dg is, the better this rule is satisfied. The better it is satisfied. With this one, we can define its joint probability. Right? The overall framework is this one. First, you have a knowledge base. Then you have a rule mining procedure. If you don't, in our numerical test, we do not have this one. No, do not have this one, but we have rules. We have rules in this one, and rules in this one. You have many rules. Then, using our embedding techniques, we transfer, project the entity and the relation to low-dimensional space. Then, using embedding-based method, we give scores for them. Here, between 1 and 0, you have scores. Using these scores, you can define the loss based on the distance to satisfaction of the rules. Then you can define the joint probability. Then you do the overall optimization using the EM algorithm. Here, the EM algorithm is based to say the weights can also be optimized. If the weight is fixed, you only use each step to optimize the embedding. Okay. Here is the results. This 1, 2, 3, 4, 5 database, 5 data sets. Ours in the first 1, 2, 3, and 1, 2, 3 are the best. But in the last two, we are not. Why? This one is better than ours because they have a rule mining procedure. They can mining more rules than ours. We have fixed rules. They can have a procedure to mining rules. They have more rules than us. So that's why their performance is better than ours. Okay. And also this results. Embedding-based methods are pure data-driven. You need to have many data to find to get a higher accuracy. If you don't have many facts, you observe only small number of facts, but you have many rules, you can still get higher accuracy. Right? That's the deep learning can leverage implicit prior knowledge compactly encoded in the rules, achieving significant improvement in the reasoning performance by using only a small number of logic rules. Okay, last section. Today we have a large language model, right? People say, oh, large language model can do the reasoning in very complex tasks, just as humans do, right? But the techniques like promoting the model and to the think step by step or chain thought, something like that, they can boost the performance on math, logic, coding tasks, creating very impressive results, right? But a closer examination reveals a more nuanced picture. This paper is 2024, from Apple. They did a systematic realistic check on the reasoning capability of SOTA LMs, large language models. What they find? They developed a controllable puzzle environment. This consists of a suite of auto-generated classic logic puzzles, just like Tower of Hanley, river crossing puzzles, something like that, with various and controllable difficulty levels. These specific puzzles instance were excluded from the model's training data because models always memorize, right? They don't want to memorize to cheating. So when they do the test, the model need to make sure the model sees the data for the first time. Okay. Not only whether a model solved the puzzle, they also analyze how it solves the problem. and also analyzing the model step-by-step reasoning traces for quality and efforts. Okay, what's their key findings? Complete accuracy compass beyond the complexity threshold. All test reasoning models hit a wall. Once the problem complexity exceeded a certain point. Initially, and the task gets harder, this LRM means large reasoning model. That's reasoning models. Showed improved performance over standard large language models. But beyond a critical complexity level, their accuracy did not just degrade. Underwent a stochastic collapse. It did not drop down, slowly down. From a critical level, direct to zero. There's no no smoothly going down there. And also, the large language model are failing in follow explicit algorithms. Even you tell them what to do, follow my procedure, do it step by step, they also fail. Okay. Large reasoning models are not executing logic steps in a procedure manner, but rather are still primarily engaged in predicting the next token, based on the learned patterns. So the limitation of large language models. And also people struggle and pay a great efforts and develop many techniques to improve their performance, including high quality data, right? They have more high quality data, including the intermediate steps to improve their performance. And also do the chain of thoughts, and also use reinforced learning, and also do the prompt engineering to get better performance. But as long as the large language models are based on predict next token, the large language model it's not said by me, it's said by LeCun. As long as the large language model are based on predict next token, it's impossible for a large language model to behave like human, reason as human do. So here we have two approaches to improve their performance with just before I talk about lots of reasoning engines, reasoning methods, right? The way is I want to say is large language models are good. Classic reasoning methods are also good. We try to combine them together to get better performance. Here is an example. Large language model with external tools. What they find? This is the iClear 2025 paper. Their results says that a significant performance collapse, just as Apple paper said, right? With self-critique, they get an answer, they critique on himself, then do the improvement, right? But the performance collapse. And significant performance gains with some external verification. If you have a very good external tools verification procedure, they can get a lot of gains, right? Even re-promoting with a sound verifier maintains most of the benefits, right? This is, say, large language model with external tools can do better. Conversely, if you have a reasoning engine with the help of a large language model, you can also do better. This one, alpha geometry and alpha geometry 2, you also must hear about it, right? It outperforms ML good medalist. Right? The method is quite simple. You have a reasoning engine. The problem is to try to solve plane geometric problems in the ML context level. You have a reasoning engine, right? But the reasoning engine is based on searching the solution. When the problem gets very complicated, it's very difficult for them to find the solution. The reasoning engine will fail, right? But when the large language model can help to give you a knowledge about how to search, where to search, then they can do better. In this example, you have a triangle. You want to show these two edges are equal. You want to show these two angles are equal. You need to construct this line, right? The midline to prove this one. But if you don't have this construct, you cannot prove it. The large language model can tell you to make this line. Then you can do the reasoning. You can do the reasoning, use the reasoning engine to find the solution. The idea is simple, but the efforts is very has a lot of efforts to train this model. They have a large database to train the model. But this one, the model is released, open source, but how to train the model, the data are not. Okay. This is the reasoning engine with large language model. Commercially, okay, that's the conclusion. Okay. Reasoning on knowledge graph is important. More efficient and effective tools are needed for large scale database. Large language model still suffers from hallucinations. How to combine these two, large language model and the reasoning engine together? Maybe you use integrate reasoning tools into large language model, or you use integrate large language model into reasoning tools. Both way, both okay. So it needs more investigation. Thank you.
Professor Kai, for the interesting talk. So are there any questions? So I have a general question. So knowledge graph models relationship as discrete structures. Could this be extended to continuous systems?
You mean you want to represent a graph into a continuous space?
Yeah. Do you see any potential for doing this, or?
I have no answer for now. I have no answer for now. Represent a graph in discrete space.
I was just curious. It's not my field of study. I was just curious.
Yeah, people try to use GNN to encode the knowledge, encode the graph, but I don't see any literature try to encode the knowledge graph, into continuous space. That's a good question. Maybe you're very interesting.
Any other?
Binary. It's not binary anymore. It's yeah. But right now it's between one. It's a real number. It's a real number. Yeah. Soft logic. Yeah. In the initial states, you have observed some facts, right? It's set true. Other all facts are assigned to 0. That's the initial states. Yeah, if the relations are sparse, mostly the true states should be 0, right? That's why we guess it's 0. Then we. But in the popular TOEFL, PSL, some other solvers, you need to grounding it first. You need to store the 0. The server even doesn't work. It gets stuck there. If you run the server, you can see that. Yeah, that's just stuck in the grounding procedure and never goes to the solving procedure. Yeah, that's a memory issue. You don't want to. Actually, that's what we do. We do not store them. We only store the validity clauses. Right. Oh, we store the truth values for the facts, but we do not store the grounding. The grounding actually is the numeric costs for grounding are very a lot, actually. Yeah. Okay.
So your method may deal with first order logic. For your method named maybe M being E, right?
Yeah.
Yeah. So is it possible for the method to deal with the second order logic? You know the second order logic cannot be separated from mathematics.
Yeah. It's in current literature, people are still struggling in first order logic, but there are some references on the second order logic, but I did not look into it yet. Yeah.
There's one more question.
Yeah.
Please join me.
Yeah. Yeah. Thank you.